So in this lecture I want to talk about logarithmic functions and relate them back to exponential functions. In fact, we'll see that, that logarithms are actually the inverse of exponential functions. So let's start with something, a specific example. We have log base 2 of x, and we're going to say that that's y. Y equals log base 2 of x. What does that mean? Well, what it means, like in other words, how we would find y, is we're saying that 2 to the y equals x. We take this y raised to that power. So what we're saying is it's the power that we would raise to get x. All right? So let me just give you a few examples of that. So for example, if I took log base 2 of 1, then that would equal 0 precisely because 2 to the 0 equals 1, right? So log base 2 of 2. So what we're saying is 2 to what power is 2? Well, that would be 1 because 2 to the first power is 2. All right, how about log base 2 of 8? Well, that would be 3 because 2 cubed equals 8. One more example, log base 2 of, let's say, 0.25. All right, 2 to what power? 2 to what power gives me 1/4? All right, well, it's negative 2, right? Because 2 to the negative 2, that's the same as 1 over 2 squared, which is the same as 1/4. Okay, so this is just kind of reviewing what does this notation mean when we say logarithm. Something that was left out of the exponential function lecture is that we have a special base, or a special base for the exponent. So if you have an exponential function, there's a very special base, which is the base e, which is an irrational number, which is approximately 2.718. So the function e to the x is a special function, and we'll see in calculus why e to the x is so important. But instead of writing log base e of x, it's called the natural log, and we denote it this way. So just to kind of make that connection, this is a special base that we call natural log, and we mostly work with natural logs in mathematics and in calculus. So important to understand what that means. All right. The other thing then, and I've kind of alluded to this already. Well, not really alluded. I just kind of said it. Is that y equals 2 to the x is the inverse of log base 2 to the x. Notice that if what this means is 2 to the y equals x, right? And to get an inverse, we switch the x and y, right? So if I wanted to find the inverse of this, I would switch x and y. X equals 2 to the y, which then I could rewrite as y equals log base 2 of x, because that's what it means. So if I switch x and y and rewrite it, then that shows that these functions are inverses of each other, and it's true for any base. So if I have y equals e to the x, then its inverse is the natural log of x. In general, if I say more generally, let some function be of base b, then its inverse is log base b of x. All right, so let's look at a few properties of logarithms. First is that log, and I'm going to do these more in general right now, but I'll give you some examples using natural log, but log base b of 1 equals 0, all right, because b to the 0 equals 1 regardless of what b is, all right? So now the bases, or we're going to have the same kind of restriction on the bases as we did with the exponentials, which is, so I'm just going to kind of put this in here, that these have to be greater than 0. We don't allow the bases to be negative numbers. That would kind of get haywire, but But for any number b that's positive, b to the 0 is 1. All right, so in terms of natural log, that means that natural log of 1 is 0. These things that I'm putting over here, especially in terms of natural log, are going to be really helpful as we go forward in calculus. So if you don't already know them or if you've forgotten them, here's your review. Okay, how about log base b of b? All right, well, here's an example of that right here. Right, if we take log base 2 of 2, we're basically saying that 2 to the first power equals 2. So that will always equal 1, right? Because any number raised to the first power gives you back that number. Okay, so this is because b to the 1 equals b. In terms of natural log, we're saying that natural log of e is 1. See, it's a little less obvious here, and this is one of the reasons I want to point it out, because when we see ln, we don't see this base e. It's implied. So, anyways, since we know that this is what it means, then of course natural log of e equals 1. The third property is that log base b of b to the x, well, we're saying b to what power is b to the x? Well, of course that has to be x, right? Because b to the x equals b to the x. All right, so this means that the natural log of e to the x equals x. And this is, again, true in general, so for any x. Another example might be the natural log of e cubed equals 3, because we're just saying e cubed equals e cubed. All right, let's take a look at a graph of a log function. And let's start with what we know about exponentials. So we know that the y-intercept of an exponential function, and let's in this case allow our b to be greater than 0. So we have something like this. Okay. And in general, for logarithms, we restrict the base to be numbers that are greater than 1. So if this is b to the x, we know that this point right here is 0, 1. That's true no matter what the base is. We know that the y-intercept is 0, 1. So that means that for the logarithm function, then we know that the point 1, 0 has to be on that function. All right. We also, let me just go ahead and put in our line y equals x here, because we know that we're going to reflect. So this is y equals x. We know we're going to reflect, to get the inverse of the graphically, we're going to reflect this across that line. So it's going to look like this, sort of. All right, so there's just a reflection across the line, y equals x. So first, in terms of b to the x, we knew that the domain was all real numbers, right? And we also remember that the range, we said, was from 0 to infinity. All right, this is true for any b to the x. I'm just going to change this to e, because the logarithm that we look at the most in calculus is natural log. So we might as well go ahead and just call this e to the x. These are still true because it's true for any base, so it's true for base e. Domain is all reals, and the range is from 0 to infinity. So again, here we're looking at the exponential function here. So then the domain for the natural log function is going to be 0 to infinity, right? So this is the y-intercept here is an asymptote for this graph. We can take numbers closer and closer and closer, but we can't, natural log of 0 or log to any base of 0 is undefined. And this is because we can't, there's no number that we can raise a number 2 and get 0 out of it. All right, and then in terms of the range, well, the range is going to be all reals. So this kind of levels off quite a bit, and it grows very slowly, but it will continue to grow forever, so it covers the entire y-axis in terms of values that we can get out of this function. We've already said here we knew that 0, 1 was on the graph, so here 1, 0 is on the graph. Okay, the other thing I want to talk about in terms of e to the x and natural log is, since they are inverses, then we know that e to the natural log of x equals x, because that's just putting in natural log in here for x, And since they're inverses, we know that if you put one function into the other, you get back x. Likewise, if I took natural log of e to the x, I would get x. And we actually already talked about that on the previous page, wherever it went, right here. So there's more than one way to understand this. One way to understand this is just that it's an identity, right? We're saying e to what power is e to the x? Well, e to the x is e to the x. That's just an identity. But also, because they're inverses, we know that this would be true. So these are a couple of identities that will be good to keep in mind because they're useful for solving different types of equations. So I want to just talk about a few more properties of natural log and then go through just a few problems that give an example of how you might use them to solve a problem. So the natural log of x times y is the natural log of x plus the natural log of y. All right, and this is because e to the x times e to the y equals e to the x plus y. So when you multiply the bases, you add the exponent. So that's kind of what's going on here. This multiplication turns into addition. Likewise, natural log of x over y is going to be natural log of x minus the natural log of y. And again, that's because if I had e to the x over e to the y, that would give me e to the x minus y. And then something like natural log of x to some power z, we can take this power and bring it out front. This is a really useful property of natural logs. So z times natural log of x. Where this comes from is if I had e to the x raised to the z power, this would be e to the x times z. All right. So raising it to a power, we can rewrite it as multiplication. Okay, so let's just see a few examples of these properties in action. So if I had natural log of the square root of x to the fifth, one of the reasons I want to do this example is just to remind you that the square root is the same thing as x to the 1/2 power. All right, so then I can rewrite this as natural log of x to the 5/2, which then I can rewrite as 5/2 natural log of x, right? So power to a power, I multiply to get the 5/2, and then I can bring this out front by our properties of logs. Then another one is if I had something like 3 natural log of x plus 2 natural log of y minus 4 natural log of z. And what I'd like to do in this case is try to rewrite this as a single natural log. So the first thing is I can take these in the same way that I could take the power down out front. I can bring these and rewrite them as power. So I would have natural log of x cubed plus natural log of y squared minus natural log of z to the 4th. And then here, the sum of two natural logs is the same thing as rewriting this natural log of x cubed times y squared minus natural log of z to the 4th. And then this subtraction, I can put this in the denominator, so I write this as a single term, natural log of x cubed y squared over z to the 4th. Okay, now I just want to do a couple examples of how we might solve equations using natural logs. So let's look at something like natural log of x squared equals 8. All right, now this can come out front, so I've got 2 natural log of x equals 8. Divide both sides by 2, I get natural log of x equals 4. And I want to use now the property that e to the natural log of x equals x. So if I raise this side, if I make this the exponent of e, then I need to do the same thing on the other side. So I get e to the 4th. So I make this e to the natural log of x equals e to the 4th, but e to the natural log of x is just x. So I could crunch it on the calculator, but that's just our number, that's our answer. One other example, if I had something like e to the negative 2x equals 5, now I want to use the property that the natural log of e to the x is x. And that's true for whatever I put in for x here. Anything that would be up here as the exponent, if I take natural log of e to that, I get back that. So I want to take natural log of e to the negative 2x and I'll take natural log of this side as well. But using this property, that's negative 2x equals natural log of 5. So then I get x equals negative 1/2 natural log, just natural log of 5. All right, so I could just punch that in the calculator to figure out what number that is, but this is, at this point, I'm done. I have a number that would be the solution to this equation. So whatever number I would have here, I could put it in for x, and I would indeed find that these were equal. So that's just that's what I wanted to cover in terms of logarithms, the relationship with exponential functions and how they're inverses, and then how we can use properties of logs to help solve equations.